Hi, in this video, I'm going to derive the power rule using the definition of derivative. My hope is that you understand it and you understand how valuable the power rule is by the end of this video. So to begin, we're going to take a look at taking the derivative of x raised to the exponent n with respect to x. So the definition of derivative is f of x plus h minus f of x all over h, limit as h goes to 0. All right, so to apply the definition, remember, this tells us to go to our function and replace every occurrence of our input variable with x plus h. So here's our input variable, and we're going to replace that with an x plus h. So we have x plus h raised to the nth. Then it asks us to subtract f of x, our original function. So that is subtracting x to the n. Place the whole thing over h, limit as h goes to 0. Now that looks pretty simple, and it's not too bad, but we have to know how to expand this binomial right here. Okay, there's several ways we can do that. I'm just going to go off of our background and look at some patterns here. So I'm going to scroll down for a second. And I have x plus h, and I expanded that several times. So right here, x plus h raised to the 0. Well, anything raised to the 0 is 1, correct? X plus h raised to the first power. Well, first power just means we just have one of those. So we have one of those, and I went ahead and put the coefficients in. So then we have x plus h raised to the second power. Okay, let's go ahead and use the shortcut that maybe you learned in Algebra 2 or somewhere. So right here, if we were to raise that to the second power, we have x squared, we have h squared, and then to find the middle term, we multiply those two together and double it. Okay? All right, so we have x plus h to the third. You can check that on the side if you'd like, but this is what that is. Expanded, x plus h to the fourth, x plus h to the fifth. Okay, so then I took what I've learned here, and we're going to go ahead and try to expand x plus h to the nth. Okay, some key patterns. Let's go ahead and take a look at this one, for instance. Okay, I'm raising this to the fourth. So that means we have x to the fourth, and look at the pattern we have here. We have x to the fourth, we have 1 less x, we have 1 less x, 1 less, until we're out of x's. Same thing with h to the fourth. We have over here h to the fourth, h to the third, h to the second, until we run out of h's. Okay, then we have these coefficients. We could talk about those a little bit later. I don't actually need all the coefficients. I'll explain in a few minutes. So I'm just going ahead and I label these coefficients as, okay, so this term, my coefficient's 1, and this is my first, second, so on coefficient other than 1. So we'll talk about those in a few minutes. All right, so let's go back up to here, and let's go ahead and expand x plus h to the n. Okay, we're going to expand this right here. X to the n, okay, x to the n minus 1, x to the n minus 2. We have 1 less each time. This just means we're going to follow the same pattern. Then we have x, and then we're down to no x's. All right? Same thing with our h's going backwards. We have h to the n, h to the n minus 1, following the same pattern. We have h to the second, h, and then we have no h's here. Okay, so our coefficients, our first and our last coefficient is 1. All right, and then we'll talk about what these coefficients are maybe a little bit later. So we have, okay, first coefficient here, second coefficient here. Okay, our coefficient would be sub n minus 1, and we already have our coefficient of 1 right there. Okay, so I expanded this binomial right here. Now we're supposed to subtract x sub n. Okay, so minus x sub n. This is all over h, limit as h goes to 0. Okay, right off the bat, I can see that we have 1x to the n here, and we have negative 1x to the n there. Those will cancel. And if you look at all the rest of the terms, they have an h in common. So I can factor out a common h. If I factor it out of here, that leaves me c sub 1, x raised to the n minus 1, all over h, limit as h goes to 0. So this h and this h can cancel, which now is not indeterminate, so I'm allowed to apply the limit. So I'm going to put 0 in for all the other h's. Well, remember, 0 times anything is 0. So let's go ahead and put 0. Okay, so there's no place to put a 0 in here. But right here, I'm going to put a 0 there, 0 there. Every term besides this first term has an h, which means every term is now going to cancel. Because I put a 0 in there, 0 times anything, I put a 0 in there, it's gone, put a 0. All of them are gone except for c sub 1, x raised to the n minus 1. That's the reason why I tabled the coefficients for now. We only have one to discover, c sub 1 here. So far we have the derivative of x to the n with respect to x is equal to c sub 1 x raised to the n minus 1. Let's find out what c sub 1 is. Well, there's another pattern that we haven't discussed yet. Okay, and that pattern is when I'm raising it to the second power here, you can see that my coefficient there is 2. When I raise this to the third power, this has a coefficient of 3. Fourth power, this has a coefficient of 4. You see the pattern. So if this is n, then this right here, c sub 1, is n. Let me modify what we have here. Okay, so we have the derivative of x to the n with respect to x. We found out that c sub 1 is n, x to the n minus 1. Okay, to wrap this video up, I'm going to show you how useful this is with one quick example. Suppose I have the function f of x equals x to the 99. And I try to find the derivative by using the definition of derivative. It would look something like this. X plus h to the 99 minus x to the 99 over h, limit as h goes to 0. Which means I would have to expand this binomial 99 times. Totally unreasonable. But with the power rule says that whatever this exponent is right here, that I just need to move it in front as the coefficient and subtract 1 as my new exponent. Simple. So my derivative then would be 99 x to the 99 minus 1 is 98. very quick as opposed to expanding a binomial 99 times. Hopefully this video helped you understand where the power rule came from and how useful it is. If this video was helpful for you, please give it a like, subscribe, and be on the lookout for other videos that I've created with the purpose of helping you navigate your calculus courses. Thank you.